Chapter 12 is about oscillatory motion. Objects that undergo a repetitive motion back and forth around an equilibrium position are called oscillators. The time to complete one full cycle, or one oscillation, is called the period, capital T. And the number of cycles per second is called the frequency, F, and it's measured in hertz. So we have the formula: frequency is equal to the reciprocal of the period, or the period is equal to the reciprocal of the frequency. And 1 hertz is our SI unit for frequency, and is equal to a cycle per second, or 1 second to the minus 1. A particular kind of oscillatory motion is simple harmonic motion. In the figure, an air track glider is attached to a spring. The glider's position measured 20 times every second. The object's maximum displacement from equilibrium is called the amplitude of the motion. In this example, the amplitude of the glider's oscillation is this distance. Also note that the shape of the function that describes simple harmonic motion is that of a sine wave, as illustrated in the plot. So in this quick check, you're asked which oscillation or oscillations is simple harmonic motion. And the answer is none of these, because none of these are described by a sine wave. In the images shown, the top image shows position versus time for an object undergoing simple harmonic motion. The bottom image shows the velocity versus time graph for the same object. So, I repeat, the top image is position versus time, and the bottom image is velocity versus time. The velocity is 0 at the time when the position is at the maximum amplitude, A. These are the turning points of the motion. The maximum speed, V max, is reached at the time when the position is x equals 0. As we can see on the plot, at when x is equal to 0, the slope of the line is the steepest. And so the velocity is the maximum. If the object is released from rest at time t equals 0, we can model the motion with the cosine function. X as a function of time is equal to the amplitude times the cosine times of omega t. Cosine is, as you know, a sinusoidal function. Omega is called the angular frequency and is defined as 2 pi over the period. And the units of the angular frequency are radians per second. And it's equal to 2 pi times the frequency. In simple harmonic motion, the position of the oscillator is given by the equation the amplitude times the cosine omega t, which we can rewrite as a times the cosine of 2 pi over the period times t. And we can also write as a times cosine of 2 pi times the frequency times t. Using the derivative of the position function, we find that the velocity is dx dt. If we take the derivative of a cosine 2 pi over the period times t, we get minus 2 pi times the amplitude over the period times the sine of 2 pi t over the period. And if we take the derivative of this second expression, a times the cosine of 2 pi f t, we see that the velocity is equal to minus 2 pi f a times the sine of 2 pi f t. Or it's just simply taking the derivative with respect to t of the first expression equal to minus omega a times the sine of omega t. All three expressions are valid expressions for the velocity as a function of time. Looking at this expression for the velocity as a function of time, we see that it is at a maximum when the argument of the sine function is equal to pi over 2. Then V max is equal to plus or minus omega times a. Example 15.1 involves a system in simple harmonic motion. An air-track glider is attached to a spring, pulled 20.0 centimeters to the right, and released at t equals 0 seconds. It makes 15 oscillations in 10.0 seconds. We're asked to find what is the period of the oscillation, what is the object's maximum speed, and what are the position and the velocity at t equals 0.800 seconds. And in this example, we model the object as an oscillating on a spring, and it's in simple harmonic motion. So to solve, we use the information given to us that the oscillation frequency is 15 oscillations in a time of 10.0 seconds. So that's 1.50 oscillations per second, or 1.50 hertz. Thus, the period is the reciprocal of that, which is 0.667 seconds. The oscillation amplitude A is 0.200 meters. Thus, the maximum velocity is equal to 2 pi A over the period, or 2 pi times 0.200 meters divided by 0.667 seconds, or 1.88 meters per second. Part C of the example, we note that the object starts at x equal to plus a at t equals 0. This is exactly the oscillation described by equations 15.2 and 15.6. Plugging in the numbers for t equal 0.800 seconds, we solve for x equal to 0.200 meters for the amplitude times the cosine of 2 pi times the time, 0.800 seconds, divided by the period, 0.667 seconds. And when we do the calculation, we see that it's equal to 0.0625 meters, or 6.25 centimeters. The velocity at this instant of time is given by the equation v is equal to minus v max times the sine of 2 pi times the time divided by the period. And putting in the numbers, we find that that velocity is minus 1.79 meters per second, or minus 179 centimeters per second. So at t equal 0.800 seconds, which is slightly more than one period, the object is 6.25 centimeters to the right of the equilibrium. And moving to the left at 179 centimeters per second. Notice the use of radians in the calculation. Example 15.2 involves finding the time. A mass is oscillating in simple harmonic motion and starts at x equal a and has a period capital T. At what time, as a fraction of this period, does the object first pass through x equal 1/2 a? If you recall the figure of the cosine function, the object passed through the equilibrium position, x equals 0, at t equal 1/4 the period. That's 1/4 of the distance in 1/4 of a period. You might expect it to take 1/8 of the period to reach a half of the amplitude, but this is not the case, because simple harmonic motion, the simple harmonic motion graph is not linear between x equal a and x equals 0. So we have to use the function x equal to a cosine 2 pi times the period time over the period. So we first write the equation with x equal 1/2 a. X is equal to a over 2, which is equal to a times the cosine of 2 pi times the time divided by the period, and then we solve for the time. T is equal to the period divided by 2 pi times the inverse cosine of 1/2. And when we solve that, we get 1/6 of the period. So when we assess this example, we note that the motion is slow at the beginning and then speeds up, so it takes longer to move from x equal a to x equal to 1/2 a than it does to move from x equal 1/2 a to x equals 0. Notice that the answer is independent of the amplitude. And that concludes this video.